Hi, if you don't know me, my name is Ryan, and the entire purpose of my channel is to help you pass the FE Mechanical exam. Today we're going to be going through the solution to this problem using the official FE reference manual. You can try this problem interactively for free, as well as every other problem that I've solved in my FE exam playlist, clicking the first link in the description below. I highly recommend you try the problem for yourself, since that's the only way that the concept is going to be refreshed in your mind and that you'll be ready for a problem like this on test day. I hope you tried the problem. Now let's get into the solution. It says a thin disk with a mass m and radius r is supported by two pins and suddenly has a failure of the upper pin support. What is the angular acceleration of the disk just after failure? Okay, again, another FE dynamics problem. One of my favorite topics. Excited to be doing this problem. Okay, first thing we know is that it's a thin disk. That upper support collapses, so it's no longer there. If we were to draw the free body diagram, this diagram on the left, what we know is that we'll have a vertical reaction, a horizontal reaction. Let's call those Rx and Ry. You can see my set of unit vectors down here. We'd also additionally have a weight term, which is just the total mass m times gravity. So we successfully drawn the free body diagram here. These rigid body dynamics problems are pretty simple once you understand the kind of procedure that you have to go through. Now, what I like to do is something called the double diagram approach or D'Alembert's principle, where we draw a free body diagram as well as this diagram called an inertial force diagram. Now, for the inertial force diagram, there's just a few steps that you need to remember. The first thing is that on the free body diagram goes forces. On the inertial force diagrams, that goes inertial forces. That's forces due to motion. The first thing that we need to do is place the inertial couple. The inertial couple is the mass moment of inertia about the centroid of that body, or the mass center of that body, times alpha. That's the inertial couple. I drew it clockwise since alpha is clockwise in this scenario. Right, the disk is going to fall down, so it makes sense that the angular acceleration is clockwise. Once we place that inertial couple, we know that we can place the inertial force. That's just the mass times the acceleration of the mass center. Having the inertial force diagram and the free body diagram makes these problems super simple, because all we do is we can sum the forces on the left-hand side diagram, the free body diagram, and set them equal to the right-hand side, which is the inertial force diagram. Same thing for moments. We take a moment, for instance, at this pin reaction, which is what we're going to do to get rid of all those reaction forces on the left-hand side. We do the same thing in the inertial force diagram and set them equal to each other. So that's the general procedure. Now, even if we take a moment here, the equation that we're going to end up with, the sum of the moments about that reaction point are, let's say clockwise moments are positive. That must be equal, on the left-hand side, it's equal to mass times gravity times the radius, r. That r is the moment arm. That is a clockwise or positive moment contribution. That must be equal to the moment produced by the inertial force diagram, which is the mass times the acceleration of the mass center times the radius, plus I c alpha. That's due to the inertial couple. Now we're going to need some information here. First thing we need to do is we need to figure out the motion of that center, this center point right here. Now, fundamental to understanding a lot of different types of motion on the FE exam is understanding simple circular motion. you can see that this centroid, or the mass center of this body, is going to have circular motion. It's going to be a fixed motion path. When you have an object that's experiencing circular motion, the motion in the tangential direction is given by r alpha plus r omega squared in the inward pointing normal direction, where this would be the tangent direction, and this is the inward pointing normal direction. Let me show you where exactly that is on the FE reference manual. That's something that I would memorize for sure. Okay, firstly, if we look here, we have plane motion of a rigid body. This makes sense, right? We're looking for accelerations. We have forces. We're going to be using equations of motions relating to a rigid body or thin disk. And essentially, we're using this second equation right here. We also need to know about some of that circular motion information here. It says plane circular motion. Now, I would just memorize this, right? But if you see the acceleration right here and the speed, we're focused on the acceleration. The acceleration in the tangential or the theta direction is equal to r alpha, and in the radial direction, it's equal to negative r omega squared. That's the inward pointing direction, right? That's the direction of our normal. Okay, now that we have some of that information, we can replace this mass times the acceleration of the mass center term with mass multiplied by r alpha. Note that at this instant, since this pin support just experienced a failure, there's no angular velocity, right? It was just still, it's still still. The only thing that's going to happen is that it has an acceleration, an angular acceleration. But because it's actually not moving just at this instant, the omega is 0. So that means that this term right here is 0. We just have that r alpha term. Let's go ahead and replace that in our equilibrium equation. Right here is where we're replacing m times r alpha, and we have an additional r from right here. So that's mr squared alpha plus the next thing that we need is the mass moment of inertia of a thin disk about the z-axis perpendicular to the page. So let's see if we can find that. Now the mass moment of inertia is at the end of the dynamic section. We're looking for a thin circular disk. This looks like our picture right here. The moment of inertia about the z-axis, the centroidal z-axis, which is shown right here, is equal to 1/2 mr squared. So that's information that we're going to need. Let's replace that information right here. The mass moment of inertia about the centroid is equal to mr squared over 2 times alpha. If we work out this right-hand side, what we have is that we have 1 mr squared here and 1/2 mr squared here. We'll have 3 over 2 mr squared alpha. That must be equal to the moment produced by the free body diagram, which is just mgr. If we solve for alpha here, we see that the mass is going to disappear, as well as one of those radius terms. What we have is g over r multiplied by 2/3. This is equal to alpha. Plugging in r equals to 1 meter and g equal to 9.81 meter per second squared, we get 6.54 radians per second squared. Let's make sure the units are correct on that. The units of g are meters per second squared, and the units of the radius r is measured in meters. We have a dimensionless or radian terms on the top, per second squared on the bottom, so this looks like the correct answer here. If you're enjoying this video thus far, please leave a like and subscribe for more content like this. I'd really appreciate it. Let's go ahead and check this answer. Okay, we got it correct. Okay, I have some of those relevant references you can see here in the solution portion here. Let's quickly review the solution and talk about our thought process. We have a rigid body dynamics problem here. We had a pin supported, 2 pin supports, one of them failed. we were easily able to construct that free body diagram on the left-hand side. And thinking about that double diagram approach, we constructed the inertial force diagram on the right-hand side. And now the problem is super simple. All we need to do is pick a moment point on the free body diagram, take that corresponding moment on the inertial force diagram, where we end up with this moment equation right here. We can easily solve for alpha, and we get 6.54 radians per second squared. We use some of these references here, like the mass moment of inertia of a thin disk about the z-axis, as well as understanding plane circular motion was super important for this problem, and recognizing that at this instant we have 0 omega. If you enjoyed this video, please consider leaving a like and subscribing. Thanks for watching. I'll see you in the next video. Goodbye.